So welcome back to our series on gases, and today we're going to look at Dalton's law of partial pressure. So the law of partial pressures considers the pressure exerted by a gas, whether it's alone or whether it's a mixture of gases. So where there are a number of gases together in a container, each gas exerts part of the total pressure, or the partial pressure. So Dalton's law of partial pressure states that in a mixture of gases, each gas exerts the same pressure as if it were present alone, so that the total pressure is equal to the sum of the partial pressures exerted by each gas. Let's say, for example, there are 3 gases in a container. So the total pressure, or P total, would be equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. This is Dalton's law of partial pressures. So let's consider a worked example now. If hydrogen is in a 1 litre container and exerting 300,000 Newton per metre squared of pressure, and is added to a 1 litre container with nitrogen exerting 400,000 Newton per metre squared of pressure, calculate the final pressure in the container due to the mixture of gases. So remember, Dalton's law states that each gas exerts the same pressure as if it were present alone. So P total will be equal to the pressure of hydrogen plus the pressure of nitrogen. In this case, the total pressure, P total, is equal to 300,000 Newton per metre squared plus 400,000 Newton per metre squared, which gives us an answer of 700,000 newtons per metre squared as the total pressure in the container as a result of the mixture of gases. Let's have a look at an example that's a little bit trickier. So we have a 250 centimetre cubed gas jar is filled with oxygen that was collected over water at STP, which is standard temperature pressure. Remember, the standard temperature is 273 Kelvin, and pressure would be 1 atmosphere, or if you're using millimeters of mercury, that would be 760, or if you're using Newton per meter squared, that would be 101,325. So the question is asking then is, what is the pressure of the dry oxygen given that the pressure of the water vapor is 4.58 millimeters of mercury? What volume of the total volume of 250 centimeters cubed is occupied by the dry oxygen? So let's have a look and see how we'd handle that. Let's look at this question to see what information we're given first of all. So we're told the size of the jar, 250 centimeters cubed. I know I'm filling it with an oxygen gas. I know there's a water vapor, there's a gas in there, and it's exerting a pressure of 458 millimeters of mercury. But hidden in here is also additional information. I'm given information of STP. This stands for standard temperature pressure. The standard temperature is always 273 Kelvin, and the standard pressure, because we're dealing with millimeters of mercury, I will quote it in millimeters of mercury, the standard pressure is 760 millimeters of mercury. So if we're collecting this sample at standard pressure, that means the total pressure is going to be 760 millimeters of mercury. So I have a total pressure that was hidden in here under STP. So I have a total pressure, and I have my water vapor pressure. So all I need to find now is the pressure of the oxygen. So remember, Dalton's law of partial pressure is the summation of the partial pressures to give the total pressure. So P total will be equal to P water vapor plus P oxygen. I know my P total, it's 760 millimeters of mercury because this was the condition that the oxygen was collected. I know the water vapor pressure, which is 4.58 millimeters of mercury. So just by doing some simple algebra, I can rearrange this equation to get the pressure of oxygen, my unknown on one side and all my knowns on the other side. So what I end up with is the pressure of oxygen is equal to my total pressure, 760 millimeters of mercury, minus my pressure of water vapor, which is 4.58 millimeters of mercury. This gives me a pressure of oxygen of 755.42 millimeters of mercury. So I've now worked out my pressure of the dry oxygen. The second part of the question asks us, what volume of the total volume of 250 centimeters cubed is occupied by dry oxygen? In order to do this part, what I need to consider is what fraction of the total pressure does the dry oxygen take up? To do this, I will get the pressure of oxygen and divide it by the total pressure to find that fraction. So that's 755.42 divided by 760. I will then multiply that fraction by the size of the container, which is 250 centimeters cubed. When I do this and put these numbers into my calculator, I come out with 248 centimeters cubed. So this is the volume occupied by the dry oxygen. Have a go at this one yourselves. So pause the video, try it out, and the answer and calculations will be on the following slide. A sample of helium gas in a 3-litre container is exerting 267,000 newtons per meter squared of pressure. It is added to a 3-litre container of neon and argon gas, which are exerting a pressure of 132,000 newton per meter squared and 455,000 newton per meter squared respectively. Calculate the final pressure in the container due to the mixture of gases. So remember, our P total is equal to the summation of all the pressures exerted by the gases. So try that and check the answer on the next slide. So here's the answer to that problem. You should have got an answer of 854,000 newtons per meter squared. So here's one final one for you to have a go of. And it says, a 100 centimeter cubed gas jar is filled with carbon dioxide that was collected over water vapor at a pressure of 780 millimeters of mercury. Part 1. What is the pressure of the dry carbon dioxide given that the pressure of the water vapor is 4.69 millimeters of mercury? Part 2. What volume of the total volume of 100 centimeters cubed is occupied by the dry carbon dioxide? So have a go at that, and the answer is on the following slide. So let's look at part 1. Part 1, you would have been given the total pressure. You were told the gas was collected at a pressure of 780 millimeters of mercury. So there's your pressure. Your water vapor, then, you were told, was 4.69 millimeters of mercury. And you just had to find your carbon dioxide. So remember, P total is equal to the pressure of the water vapor plus the pressure of the carbon dioxide. You know your total and you know your water vapor. So do some simple algebra to this equation then to work out what the pressure of the carbon dioxide is. And from some simple mathematics, you should have got 775.31 millimeters of mercury. Part 2, then, you want to see the fraction of pressure that the carbon dioxide is taking up. So it would have been 775.31 divided by your total pressure, which was 780. And then you multiply that answer then by the size of the container, which was 100 centimeters cubed. And you should have got an answer then of 99.4 centimeters cubed. So that brings us to the end of our series on gases. If you're interested in looking at more videos, go to my channel, which is Leaving Cert Chemistry Tutorials. Thanks very much for joining me.